Thank you so much for the introduction. Good afternoon. Today I'm going to be talking about joint work with Karan Newatia, Tao Luo, Ido Roth, and Andreas Haeberlen that looks at how to answer sensitive questions over billions of distributed records, all while providing strong privacy guarantees. So why do we care about this? Let's think about health data. There's currently about 1.5 billion iPhone users globally, and pre-installed on every iPhone is the Health app. And this app contains sensitive information: how much you sleep, how much you work out, what medications you take. And we could imagine that this information could be really useful to public health researchers. For example, we know that insomnia can have a lot of second-order health effects that can be hard to correlate and study. Public health researchers might want to know, which combination of medications do people with insomnia take the most? One approach to answering this question: let's ask Apple. Apple could then ask its users to contribute their information, it would evaluate, and publish a result. But there's a pretty big problem here. With this solution, both Apple and public health researchers could learn information about an individual's private data. One solution is to use something called differential privacy. And Apple actually does this already for much less sensitive queries. Questions like, how frequently are emojis used? With differential privacy, users send their information to Apple, and Apple publishes a differentially private result. And differential privacy is great. We now get privacy at publication, so we have privacy with respect to the researcher. But it doesn't protect user privacy at computation. Apple is still seeing everything, information that normally would be kept on device. Another approach is a system called Orchard that some of my collaborators created a few years ago. The way Orchard works is users encrypt their data, send it to Apple, and then Apple enlists a single small committee of users to privately compute and publish the result. Orchard solves some version of this problem. We now get privacy both at publication and computation, but it has two major limitations. The first is that Orchard has a fixed data flow, which means that supporting new queries beyond what's in the original paper requires writing new plans by hand. And this can be really time-intensive and requires subject matter expertise in cryptography and privacy. The other limitation is that Orchard can't actually answer our question, nor the kind of class of queries that it falls into. At the scale we're talking about, it would completely overload this small committee of users. So we want federated analytics with privacy at both computation and publication, and for a wide range of queries. And we don't want to have to write new plans to answer these queries every time we want to ask a new question, and we don't want to overwhelm any individual party in the system. So our solution relies on two key insights. The first is offloading. All of those users in Orchard who weren't on that small committee aren't doing anything. We can offload some of the compute to them. But we want to make sure that analysts who are writing these queries and have to figure out the best way to offload onto these users don't have to go bother a cryptographer every single time they want to ask a question. This leads to our second key insight: automated planning. While handwriting plans to answer queries, you can also call them query plans, is hard and takes time, automatically generating them can be fast and easy. We can find good custom protocols without needing subject matter expertise. And while these queries are very, very different from the types you see in database-style query planning, we can still draw inspiration from the field. This brings us to Arboretum, a query planner for private federated analytics. At a high level, Arboretum works as follows. An analyst submits a query to Arboretum. Arboretum evaluates and scores potential plans. The best plan is then executed by any and all of the entities in the system. This can be a powerful aggregator, committees of users, even individual users. And then a differentially private result is published. So I'm going to start with some useful background before getting into the nitty-gritty of how Arboretum works, and then go through an evaluation. So the first piece of background I want to cover is something called the exponential mechanism. And this is a way to answer categorical queries with differential privacy, so queries over a discrete domain. For example, what is the most populous zip code in the United States? The exponential mechanism has two main challenges. The first is we have to calculate a quality score Q for every element in the domain. So if we were talking about zip codes, that would be a little bit over 32,000 quality scores. Second, as the name implies, we then have to exponentiate every one of these quality scores. Both of these can be expensive depending on if you do them under encryption and if you want to do them in a privacy-preserving manner. The second bit of background I want to cover are some useful privacy tools that we use in Arboretum. The first is something called multi-party computation, or MPC. Simply, it's a way for two or more parties to jointly evaluate a function on private inputs. It can evaluate a wide variety of functions, but it has poor scalability and it's interactive. The next primitive, which has already been talked about up here, is additively homomorphic encryption, or AHE. Like was said earlier, it essentially allows us to do linear operations over encrypted ciphertexts. It's comparatively cheap, but we can only do linear operations. And then finally, we have something called fully homomorphic encryption, or FHE. You can think about it as AHE, but now we can do nonlinear operations. Additionally, it is non-interactive. However, it can be very, very expensive. So, with all of this background in mind, let's talk about Arboretum. The first phase of Arboretum is going to be writing and compiling our query. So, for our combination of medications questions, we would start by writing the query in our imperative domain-specific language. It would look pretty much exactly like this. You'll notice that there are a couple of functions that we're calling here. Things like sum, which computes a summation, EM, which applies the exponential mechanism. Arboretum supports a number of built-in functions with its domain-specific language, and many of these functions can be implemented in multiple ways. And so in order to fully consider all of the possible plans, we have to consider all of the possible combinations of all the possible implementations. What does this look like? Let's look at a toy example. So here I have an array, 5 numbers, I want to add them up. You can do this in at least 3 different ways. And you might look at this and say, well, obviously there is a best answer. However, there are actually pretty subtle trade-offs. For example, on the left, this is good if you have a single powerful aggregator that you want to do the summation. However, it doesn't parallelize super well. The 2 solutions on the right both parallelize much better. But depending on how you want to do it, that might mean more work for users and incur additional network communication costs. And so all of these trade-offs aren't clear right off the bat, as they might seem, especially when you consider how functions compose with other functions. Additionally, these trade-offs are further exacerbated when you have to consider that different parties can do different parts of a computation. So the point is that each of these options can lend itself well to different distributed assignment and different parallelization. So how do we assign these computations? Like I've said, a crucial part of Arboretum is that different entities do different computation with different encryption types. In order to assign computation, Arboretum will break plans into short sequences of consecutive statements of a query. And each one of these short consecutive statements represents a single entity cryptographic assignment pairing. So for example, we could have an aggregator do a summation with AHE, an MPC committee do the exponential mechanism, and an aggregator with FHE do some post-processing. So, seems easy enough. Why is this hard? Well, let's come back to our query. I told you that AHE is cheap. Why don't we just do that? Well, like you might remember, we have to do more than addition for the exponential mechanism. So, we're out of luck there. Okay, I told you that FHE can do AHE and multiplication. While this works, it is cryptographically sound. Turns out it could take years of compute, even for a powerful aggregator, depending on if you have a large number of users and a large number of categories. Okay, fine, let's try MPC. That should work, right? Well, it does, but it turns out if you do MPC for the whole query, you're going to force a committee to download gigabytes, if not more, of raw user data just to do an initial summation. So none of these pure protocols work. Let's make it even more complicated. Let's combine protocols. What happens if I start in AHE, and then move to FHE just for the parts that need more than addition? Well, while it again is cryptographically sound, it turns out not only do we have the same compute issues as before, now you're going to incur additional costs from decrypting from AHE and re-encrypting into FHE. Let's give it one last shot. Let's start in AHE and move into an MPC. And it turns out this is probably the best we're going to do in this case. It doesn't overload any committees or users or the aggregator. So we did this at the high level, kind of viewing the functions as single entities. Imagine doing this for every discrete operation once all of the functions have been compiled down into all of their possible implementations and for all of the possible combinations. You get a really large number of plans, all the implementations and all the possible people who can compute it and all the possible cryptography they can compute it with. So we have all of these plans. How do we pick one? So for scoring, right off the bat, I want to say, while it's really natural to want to pick the absolute best plan, we can't. We're working with billions of devices, all of which can be different, all of which have different network conditions, so it is going to be impossible for us to pick the absolute, honest-to-God, best plan. Instead, what Arboretum aims to do is to weed out bad plans as quickly and efficiently as possible. We want to recognize quickly that starting in AHE and then re-encrypting into FHE is a bad idea, and you should maybe consider an MPC instead. To do this, we use a simple cost model. We hard-coded our cost model into the tool for now, but that being said, if you wanted to customize it with new primitives, that can easily be done using an automated system such as Costco. So now that we've talked about how Arboretum generates its plans and scores them, once we have a plan, what do we do with it? Plan execution consists of 4 phases. The first is setup. Users are assigned to committees, including one that generates an encryption key. Next, we have input. All of the users encrypt and upload their query responses. And then analysis. Analytics will happen as prescribed by the plan between aggregators, users, MPC committees. And then finally, release. A final decryption committee decrypts and publishes the differentially private result. So now that we've talked about Arboretum, how good is it? In order to evaluate Arboretum, we looked at a wide variety of questions, and unfortunately, I don't have time to talk about all of them, so instead I'm going to focus on these top 3. For the rest, I encourage you to see the paper. So first off, what queries can Arboretum support? So previous work in this area, out of this list of queries, could only support these bottom 3. And that is with the major caveat that it could only support them if you had less than 10 categories. Not only does Arboretum support this work, but we expanded the number of categories supported for these queries by over 1,000x. So we went from 10 categories that could be supported to over 32,000. Additionally, we evaluated these 7 new classes of queries. But our DSL means that we can support even more. These classes are just the ones that we found most commonly in the literature. Next, we looked at the costs incurred by Arboretum's planning. So the planning cost here is consistently under 4 minutes. The worst case that we evaluated is going to be this median query, and it generates and evaluates over 1 million plans in a little less than 4 minutes. And I want to emphasize, this is versus the alternative of doing it by hand, of writing these query plans by hand. In the past, writing a query plan for a single query was a paper in and of itself, and that could take weeks, if not months of time. Additionally, I want to point out that the planning time is less than 0.1% of the plan execution time. These plans are designed to run over the course of hours, and so we feel that this is a pretty reasonable cost to incur. Finally, we wanted to look at the quality of Arboretum's plans. Arboretum's plans require less work for committee members. So here we have the maximum amount of traffic sent by committee members and the maximum compute time. And we compare this to previous work, specifically Orchard, for the queries that it was able to support. We see that consistently, Arboretum's plans require less work both in terms of maximum traffic sent and in terms of total compute time, in some cases as much as an order of magnitude less. Again, I want to emphasize, not every user will be on a committee. So this amount of work isn't going to be asked of every single user in the system. Instead, you can kind of think of this as an absolute worst case for the user. So we are dramatically improving the worst case scenario for users. So, in summary, we wanted federated analytics at a large scale for complex categorical queries, all while providing strong differential privacy guarantees. We didn't want to have to write plans by hand, and we didn't want to overwhelm any individual party in the system. By realizing that we can have users contribute to the computation, and we can explore the plan space automatically, we end up with Arboretum, which provides query planning for a wide range of differentially private queries, scales to billions of users, and quickly finds plans that outperform hand-tailored solutions in previous work. And with that, thank you for your time, and I'm going to open it up to questions.
Please.
Hi, this is Derek Leung from MIT. My question was, what's the threat model for these servers and other users? Are they malicious or like honest but curious? And does that affect the kind of planning you can do with MPC?
Yeah, so we assume occasionally Byzantine kind of honest but curious. So we assume that the aggregator is correct at startup initially, and then we assume that again it is honest but curious.
Great, thank you.
Yeah.
No question? No, I have a question about the query planning.
Mm-hmm.
So you know that there's lots of query optimizations from the database community. I'm wondering if your query planning is optimal, and what kind of optimization can be applied for your query planning?
Yeah, no, that's a really great question. So our primary focus here was on the ability to generate plans with tolerable costs, but we totally acknowledge that I think there's a lot of work in the database literature, particularly distributed databases, that we could incorporate to get that planning time down significantly.
Hi, please.
Thanks so much. This is Emma Dodderman from UC Berkeley. Really great work. I'm curious if you take into account different types of MPC protocols, like arithmetic circuit-based or Boolean circuit-based?
So we only use arithmetic circuits, and we only use them for majority honest protocols. One thing to look into in the future, though, is whether we can expand that.
Yeah, thanks so much.
Hello, also a quick question. I'm Reggie Frank from UC Berkeley. I was wondering if you took into account the performance cost of maybe failures in the network, and if that might have been used in the planning phase as well.
Yeah, so we do tolerate dropouts, and we do take that into account. However, that's less in the planning phase and more in the sort of underlying cryptographic primitive design phase. Specifically, we make sure to configure the MPC protocols so that they can tolerate up to 15% dropout.
Thank you.
Okay, the last question.
Hi, Richard Black, Microsoft. Why not go for the centralized solution with confidential compute?
Sure. So I think the issue is that kind of going for this centralized solution is just really, really expensive, particularly for these exponential mechanisms. So, we talked a little bit about the what is the most populous zip code, which can have a kind of easy quality score to compute. However, for some of these other use cases, such as median, these quality scores are quite complex, and so doing them with sort of confidential compute or with, doing the whole thing with fully homomorphic encryption, we found that it would take, years worth of thousands of core hours. And so we couldn't find a way to do it that made, that was kind of tolerable cost profile.
Thank you.
Okay, so let's thank the speaker again for the great talk.